So today we're going to start chapter 5. We're going to take a look at perpendiculars and bisectors. So way back in chapter 1, okay, we learned that a segment bisector basically crosses a segment right at its midpoint. Okay? So a segment bisector is just could be a line, it could be a ray, but it intersects a segment right at its midpoint. Well, perpendicular bisector, okay, it's similar, but it does two things. One, it intersects a segment at its midpoint, but two, it's also perpendicular to the segment. Okay, so a perpendicular bisector could be a segment, a ray, or a line, and it's perpendicular to a segment right at its midpoint. Okay, so something like that. It doesn't look like we have any triangles in that picture, but there are. If we add in a couple segments, we could make some triangles. And we're going to have a theorem that we're going to prove, and it's going to use some triangles. Okay, so in this picture, it's actually line, not ray. Line CP is a perpendicular bisector of AB. Okay, how do I know that by looking at the picture? Well, first of all, they've marked it perpendicular with that square in the corner. And second, they marked AP and BP the same length. That's how I know P is the midpoint. Okay, so any questions on the definition of a perpendicular bisector? Yeah.
Can you actually bisect a line?
Can you bisect a line?
Yeah.
No, because the line really goes on forever. But you can bisect a segment. Yep.
Well, if the line goes on forever, wouldn't any perpendicular line be bisected?
Yeah, well, that's a good point. If it goes on forever, where's the middle? Could it really be anywhere you want? You know, it's kind of like looking at a circle. Where's the start? Where's the end? It really isn't. So, yeah, it's an interesting question. A little more philosophical. But, yeah, so we'll stick to bisecting segments. That we can do. Okay, equidistant. Okay, what word do you see there that might be familiar to us? Or it's kind of similar to what other word? Yeah?
Equal.
Equal, yeah, equals. This has something to do with being equal. So a point is equidistant from two other points if the distance to each point is the same. So if I said I'm equidistant between the front wall and the back wall, that means that I would be standing exactly halfway between a point on the front wall and a point on the back wall. So I'm equidistant between 2 points. Okay, so here's an example. Point C is equidistant from A and B. The distance from A to C is the same as the distance from B to C. That's equidistant. Okay, any question on that? So let's look at a theorem having to do with perpendicular bisectors, and it's going to tie in this idea on the other page. Okay, it's a perpendicular bisector theorem. It says that if you have a point on the perpendicular bisector of a segment, then that point is equidistant from the endpoints of your segment. So if you have a segment, and you draw in a perpendicular bisector, any point that you put on the perpendicular bisector is equidistant from the ends of your segment. Okay, so here's a picture. AB is a segment. C is a point on the perpendicular bisector of AB. I'm telling you that. then the distance from that point to A and that point to B is exactly the same. In fact, anywhere that I put a point, if I measure the distance from any point on that line directly to the endpoints, directly to A and directly to B, all those distances corresponding, that would be the same as that. That one would be the same as that one. Obviously, the distance gets bigger as you get farther and farther away, but the two distances to each endpoint, that's what stays the same. Okay, any question on that? And you might see it just by kind of what I drew there, how we might do a proof of that. If we draw in a couple segments, we create some triangles. Right?
Does it prove the whole thing?
Well, we're going to go through that one. Okay, we're not going to prove everything today, but we are going to prove this one. Okay, the perpendicular bisector theorem. Okay, it's the same picture I just had on the other page. So they're telling me that line CP is the perpendicular bisector of segment AB. Let me just take C and, oops, see if we can move that down a little bit. Okay, I want to somehow prove that CA and CB are the same. I'm going to prove that theorem. I'm going to prove the distance from C to each endpoint comes out the same. Okay, what did I say earlier? When you're doing a proof, it usually comes down to using what shape? Triangles. And we're usually trying to prove that the two triangles are what? Congruent. That's what we have to do here. Prove that two triangles are congruent. All right? Now, they didn't say that. They said prove CA equals CB. Well, our last step will be the CPCTC. But first, we have to show triangles are congruent. Then we can show what they want. Let's write down our statements. Reasons. Let's see if we can just try to figure out what triangles we think we're going to show are congruent. Let's write that off to the side. What two triangles do you think I'm going to show congruent here? Triangle, yep, just give me one of them.
CPB.
Okay, CPB. And who can give me the other triangle? We have CPB. Yeah? CPA. Okay, that's kind of our intermediate goal to get to that proof. Show those two triangles are congruent. Right? Anybody see anything here that I could start to use? Keep in mind, not everything that was written in the given is marked in the diagram. So you might have to look back at the given for some information as well. Yep?
CP is perpendicular to CP, the reflexive property.
Can you just say it one more time?
CP is congruent to CP.
Okay, yeah, congruent. CP is congruent to CP. That's the reflexive property. Okay, so good. We got a side. That's the reflexive property. Okay, let's mark it. Anybody see something else that I could use here? How about Luke? You see something else I could use?
You can find the length of A and C, and also B and C if they're congruent, right?
Well, that's what we're trying to prove. We're trying to prove that those dotted lines are congruent. So we got to show these two triangles are congruent. So we got one side.
So if P is perpendicular to, or line CP is perpendicular to AB, then is P the midpoint of A and B?
Well, just because it's perpendicular here, it doesn't mean it's the midpoint. But what else is segment CP? They told us up in the given.
Oh, it's bisector.
It's a bisector. The bisector part tells us that this is congruent to that. Okay? So AP and BP are congruent. What's the reason? Given. Yeah, it's given. It's the bisector. Okay, that's up in the given. Step 3. Well, now if we've got a side and a side, and remember what we said about perpendicular lines. If you have perpendicular lines, they form 4 right angles. Okay, so let's say angle APC. That's a right angle. Okay, angle APC is a right angle. And the reason? That's not the definition of perpendicular lines, but it is a theorem about them. If you have perpendicular lines, they form 4 right angles. We don't need the 2 on the top. That's not really going to help us. Okay, but we do need the 2 on the bottom. So just say 2 perpendicular lines form 4 right angles. Now I can say my 2 triangles are congruent by what theorem?
Side angle side.
Yep, side angle side. Okay, so triangle, let's go back, CPB is congruent to triangle CPA. Side angle side. Now if the 2 triangles are congruent, what do you know about the dotted segments? Yep, the dotted segments, CA. Now they said to prove CA equals CB. Whether you prove CA equals CB or CA is congruent to CB, this is saying prove the measures are the same. Okay? We basically have that. We have corresponding parts. So if I want to be kind of formal, I'll say it that way first. CA is congruent to CB. The reason is CPCTC. Corresponding parts are congruent. And if 2 segments are congruent, what does that mean by definition? Yeah?
Their measures are equal.
Then the measures are equal. Bless you. Okay, and that's the definition of congruent segments. Okay, we haven't been quite that formal about a proof in a while, but that's a very formal proof. Nothing to argue with there. That's a good proof. Okay. Any question on that? So now we don't have to prove that again. Anytime you've got to set a point on the perpendicular bisector of a segment, these dotted lines are always equal. Always.
If it was on the MCAS, do we have to still prove it?
If they asked you to prove it, yes.
Okay.
If they didn't say to prove it, you could use it as a theorem depending on the kind of question. Yeah. But they could give you a diagram. So I'll do some problems later today where I give you a diagram and I give you some numbers and I ask you to find the length of something. Now that you know this theorem, that'll help you. Okay, let's look at the converse of that theorem. We're not going to prove the converse. You could prove it very easily, almost just like we did the last one. So the theorem basically says if you've got a point on the perpendicular bisector, then it's equidistant from the endpoints. This starts out with the endpoints. Okay? It says if you have a point equidistant from the endpoints, then that proves the point is on the perpendicular bisector. Okay, so this is the converse of the original theorem.
And then it says technically if it's equidistant from the 2 endpoints, then it's a midpoint.
Then, well, it's
Because if it's
Yeah.
equidistant, it's a midpoint.
Well, not necessarily. So let's say you had this, right? And you got a point here. And all I tell you is that this segment and that segment are congruent. That green dot isn't really the midpoint of anything.
But that,
But this, yes, if you put this red dot in right here, absolutely. That is a midpoint.
but it's very easy from that point, that green point, to prove that red point.
Yeah, right, because you got a point, and it's equidistant from those endpoints. It proves it's on the perpendicular bisector, which proves that segment is equal to that, proves that's a 90. You've got reflexive property. You got congruent triangles again. Yep. That would basically be the proof if we wrote everything out formally that I just said. Yep. Any questions on the converse? Everybody have the converse of the perpendicular bisector theorem? Okay. All right, so let's try a calculation. So before you saw that theorem, if they gave you a diagram like this on the MCAS, you probably, you might not have been sure exactly what to do. So it says in the diagram MN, now they didn't draw it all the way, that's okay, but MN is the perpendicular bisector of ST. What segment lengths in the diagram would be equal? You don't have to tell me what they are. I just want to know this segment would be equal to this segment. Okay, there's a few pairs here. Anybody see one pair of segments that would be equal? Even if you didn't know the theorem, you could actually do this part right away. Which segments there are clearly the same measure? Luke?
Line TQ and line SQ.
Yeah, segments. Yeah, segment TQ and SQ, they're both marked 12. So they're obviously equal. Okay, and notice, just to kind of do a refresher on our notation, I didn't put the segment bars over it. This means that the measure of TQ equals the measure of SQ. Congruence would be written like this. This isn't what they asked for. Okay, they asked which segment lengths are equal, not which segments are congruent. Okay, so you don't need that. What else? We've got TQ and SQ. Make sure you use the fact that MN is a perpendicular bisector, so that tells you some stuff.
MS is equal to MT.
Yep, MS and MT. Because they tell you MN is the perpendicular bisector, you've got the congruent triangles right there. And I think we actually can get a little bit more info out of the congruent triangles. There might be one more pair. Yep,
TN and SN.
TN and SN. Now, don't say MN equals MN. It didn't ask you if there was any reflexives here. Obviously, that's true. But I think those are all the segments that are congruent. TQSQ, MSMT, TN, SN. Yep. Now, I didn't tell you that Q was on the perpendicular bisector. Okay, but why is it? That's basically what they're asking in part B. MN is the perpendicular bisector. If you were to keep extending line MN, why would Q have to be on it? It has to. Yeah?
MN is a line, and it goes on forever. And since MN is the perpendicular bisector, it goes through Q. And
Why though? Why does Q have to be on that bisector?
in this diagram, it has to be because it's in the same plane, I think, same line of M.
Okay, it looks
But
like if
in
you
this-
extended it, it
in
might
this
be on the
picture-
line.
In this picture, it has to be if you extended it, but in other pictures, it doesn't have to.
So you got to give me a theorem that tells you why it has to be. Even if it looks like it is, remember, it's not drawn to scale. In fact, let's just see if I extend it. It might Yeah, that one actually looks pretty good. So it's drawn pretty much to scale, but what theorem proves Q is on the perpendicular bisector? Even if it wasn't drawn to scale.
It was the last one we just saw, I think it's like the perpendicular converse thing.
Yeah, the converse. Q is equidistant from the endpoints T and S. Q is 12 units from T, it's 12 units from S. If it's equidistant from the endpoints, that proves that it's the perpendicular bisector of the segment. It's on them, okay? So the reason, since Q is equidistant from, what is it, T and S, the converse of the perpendicular bisector theorem proves Q is on Mn. Okay. Any question on that? So remember, just be careful. Even though sometimes the diagram is drawn to scale, and you can kind of look at it, but sometimes you're going to have some diagrams that are drawn completely not to scale. So you got to go by what's actually marked or labeled and use theorems, even if it doesn't look right. All right. So if I had, say, I took this diagram, I don't know if I can change it a little bit. Let's say I did that. I don't care that it doesn't look like Q is on the perpendicular bisector anymore. It still is. It's not drawn to scale. But if that point is equidistant from the endpoints, that proves that that point has to be on the perpendicular bisector. Just not a good drawing. Okay? Any question on that? All right. All right, so the next part, I'm going to look at how you measure the distance from a point to a line. So if you want to measure how far away you are from, like, say, the wall, like if I was going to measure my distance to the wall by the windows, would I measure it towards, like, the back corner? Is that the shortest distance from me to the wall?
The shortest distance between 2 points is a line.
Isn't that a straight, like,
It has to be a straight line, like, that would be diagonal, you'd be going over there.
what would that be? Anybody explain what he's saying? He's saying I'd be measuring on a diagonal if I went towards the back corner of the room.
It's the hypotenuse.
Okay, yeah, it would be like a hypotenuse. So what would it be if I went, like you said, straight towards the window, that way? It'd have to be the distance. I need a special word in here. You think you know it, Selena?
Is it on the board?
Yeah,
Perpendicular.
it's perpendicular. So when you measure the distance straight to something, you measure it straight, but you also have to measure it perpendicular. Like if I'm going to measure my distance to the front board, I don't measure it towards the calendar. I measure it perpendicular to what I'm trying to measure. Okay, so the distance between Q and line PM is QP, and this would have to be perpendicular. Okay, that's the distance between Q and PM. Any other distance that you measure is a longer distance because it's not being measured perpendicular. Okay, it's still straight, it's just not perpendicular. Okay, so that's how you measure the distance from a point to a line. It's always measured perpendicularly. Right, and we talked about this idea of equidistant earlier. We're just applying it in a little bit different way. So if you have a point that's the same distance from two lines, then we just say the point is equidistant from the two lines. Okay, and I'll draw a picture of that in a second. Okay, so if you've got a point that's the same distance from one line as it is from another line, it's equidistant from the two lines. And remember, how do you measure the distance between a point and a line? You measure it straight, but you also measure it perpendicular. Yep, measure it perpendicular. Okay, any question on that idea of how you measure the distance between a point and a line? Perpendicular. All right. So So that leads us into the last part of our theorems. We talked about the segment bisectors. Now we're going to talk about angle bisectors. Okay, what I've drawn here is angle BAC. And you know what? Let's call that D. Ray AD, that's an angle bisector. How do I know? The angles are marked congruent. Angle BAD and DAC. Okay, so if you draw a segment, divides an angle into two equal parts, that's called an angle bisector. All right, so if you've got a point on the bisector of an angle, like we do here, point D, then it is automatically equidistant from the sides of the angle. Okay, let me do the sides of the angle in red so you can see those better. Okay, so if you've got a point on the segment angle bisector, okay, like we do here, D, then that point is equidistant from the sides of the angle. Okay, so DB and DC, that's the distance from the point to the side of the angle. And it's measured perpendicular, straight to the side. Okay, not at an angle, but straight through it. Anybody have a thought what kind of triangles you have here? They are right triangles, but they're also going to be something else. Anyone notice? Yeah?
Isosceles.
Not necessarily isosceles. Yeah, they're definitely, well, they're going to be right, so they can't be acute if they're right. Yeah, could be scalene. How about if you compare the two triangles? They are going to be congruent because you've got a length matching a length. You've got a reflexive property right there. So you could use hypotenuse leg theorem, or we also have this angle. We didn't even use that. Angle, angle, side. Could look at it that way. Okay, but the point is you got two congruent triangles again. Okay, everything always comes back to congruent triangles. Okay, and the converse of this theorem is also true as well. If you've got a point that's inside the angle, and you tell me that it's equidistant from each side, you've also just automatically told me that it's on the angle bisector. So if you've got a point on the interior of an angle, and it's equidistant from both sides, then that point is automatically on the angle bisector. Why? Well, we could prove we have congruent triangles, and once we prove that angle BAD and DAC are congruent, that proves AD is an angle bisector. We're not going to go through the proof formally. At least we're not going to do both of them formally. Okay, we already did one of the theorems formally. Let's do the, I think, is this the converse? Yeah. Let's look at this one. So it says D is on the bisector of angle BAC. So, okay, they're telling you it's on the bisector. They want you to prove DB and DC are congruent. I kind of already showed you how with congruent triangles. Okay, so let's see if we can just show the two triangles are congruent. Statement one, I'm going to say DA is congruent to itself. DA congruent to DA. What's the reason for that? That's reflexive, yeah. Okay, step two, what else do they tell me? Oh, I got a right angle. Angle B and angle C are right angles. Okay. Yeah, so let's write that down. Angle B and angle C, sorry. Angle B and C are right angles. Reason, that's given. They tell me I have perpendicular segments or perpendiculars, so we know that if it's perpendicular, it makes a right angle. We could say definition of perpendicular as well, okay, but that's fine. Okay, and what else do we know? Technically, I'm not sure. It says D is on the, oh yeah, we do know. We do have some bisectors here. So how would we name the two angles that are congruent? Angle, yep.
CAD.
CAD, yep, let me write that.
AD.
CAD and BAD, yep. Angle bad. CAD and bad. All right, so those are congruent. That was given to me. It says D is on the bisector of the angle. Okay? So AD is a bisector. That was given. And I think we have enough information. How can we prove those two triangles congruent? Side, yeah. What else?
Angle, side.
Yeah. Oh, yeah, angle, side, or side, angle. Either way. So let's write down triangle CAD is congruent to triangle BAD. Reason? Angle, side. Right, and my last part. I think now we have it, DB and DC. Okay, is that a measure that they're talking about here, or is that congruence? That's a measure, so we got to say the congruence first, then we can say the measure. Anybody remember the reason we did this earlier? DB is congruent to DC.
C, D, C, TC.
Yep. The corresponding parts of congruent triangles are also congruent. Now we can say the proof DB equals DC. That's the definition of congruent segments. Okay. So now we don't have to go through that proof of that again. We've now proved what we wanted. Okay, so let's finish up with a few calculation ones and then kind of this one's like a yes-no question. Okay, so it says, looking at that diagram, I want you to tell me whether or not you have enough information to prove C is on the perpendicular bisector. Okay, so now be careful. We're kind of switching gears a little bit. We were just talking about angle bisectors before. Now we're going back to perpendicular bisectors. What would be the fact you have to know here? If you want to prove C is on the perpendicular bisector, what would be the perpendicular bisector theorem? What would have to be known here?
That from A to C.
Yep.
Well, there needs to be another point.
Well, just keep going with that. So from A to C.
Is congruent from B to C.
Right. You'd have to show that segment AC and BC are congruent or that their measures are the same. Do you have enough information in this picture? Anybody think you do? I definitely can prove that C is on a segment that's perpendicular to AB. That's given.
Oh, it's
Now, Connor said that I've got to know AC
no.
and BC are the same, which
No,
is
from the
correct.
bottom. From the bottom, from A to the
You want to label that? Sure.
D. From A to D needs to be congruent, and from B to D needs to be congruent.
That'd be a different way to do it, yes. So you either have to know from A to C and B to C, that's the same, or you have to know from A to D matches B to D. You don't know either. And no matter, you can draw your triangles, but you don't have enough information. You definitely have a side that's reflexive.
All I know is that there's a
You got a right angle in each, so you have a side and an angle. You don't have another side on the diagonal, or the hypotenuse, or the bottom. You can't prove that. So no, we cannot show C is on the perpendicular bisector of AB. Can't do it. Okay, sometimes those are the trickiest types of questions because you're not sure. You look at it, you don't know if you have enough information. But here you don't. There's no way to do it. Okay. And last one is more of a calculation. I want to find the length of VT and the length of SR. Okay, what's the length of VT here? And then Y. Denver?
8.
Yep. Why is it 8?
It's half of RT.
Okay, that is true. How do you know it's half of RT?
Because
That's not given up above or anything.
bisected perpendicular.
Yeah, we know it bisects it because look at, you got a congruence mark on RV and, or I'm sorry, VT and VR. They're the same length. And if VR is 8, then VT has to be 8. Okay, so that's 8. Now what about SR? Do we have enough information to find the length of SR? Yeah? Is there anything special about point S?
Yes.
Where is point S? How would you describe it? It's on the what?
Perpendicular bisector.
S is on the perpendicular bisector. So what does that mean? If you have a point on the perpendicular bisector, what does that tell us?
That RS and TS are the same.
Right. Okay. If you have a point on the perpendicular bisector, that tells you that it's equidistant from the endpoints. So S to T and S to R have to be the same. Okay. Now, what if I asked you to find the length of VS? You could. How would you do it?
Oh,
You could find the length of VS if I asked for it. You'd use the Pythagorean theorem. Exactly. Yep. We're not going to do that here, but if they wanted it, you could. All right, so this will be our last homework for the week. Tomorrow we're going to do the MCAS simulation and Friday as well. So 9 to 13 odd, 17, 19 to 26 all, 28, 30, 45, and 51, and there's no MCAS tonight. Just the bookwork.